Alright, so we're still in chapter 9. We're still talking about the hydrogen atom and its wave functions in particular right now, as well as its eigenvalues and its Hamiltonian operator. I've got two more of these slides set up here saying locate the nodal surface on, in this case, the 3D x squared minus y squared orbital, and then the next one will be the 3D z squared. And these are both ones that we worked exactly in the spherical harmonic portion, in the rotational spectroscopy portion of the course. There's no radial nodes on either of these. You'll notice that the function only becomes 0 at r equals 0 and at r equals infinity. But there are two two angular nodes. And if I want you to try to work these out on your own. I'm not going to work them out here in the video. I'm going to show the problems. Here's the one on 3D x squared minus y squared, and you can look at this one in the PDF of the notes, or pause here and write it down. And then there's also the 3D z squared, which we've worked out together, and I'll show you the pictures as well. If you need help with the algebra on these, there is an examples document with the PDFs in the lecture file that show the algebra worked out in a little bit more detail. But I want you to try to work them out on your own before you look at that algebra. So one of the things that we've noticed here that may help us moving forward with these kinds of problems is that the total number of nodes is always going to be n minus 1. So if I have you working on a 4f orbital, there's going to be 3 total nodes. If I have you working on a 7d orbital, there's going to be 6 total nodes. The number of angular nodes that we have, whether they're cones or planes, is going to be L. And then we can do a little bit of math there. The number of radial nodes is going to be n minus L minus 1. Now remember, for s orbitals, whether it's 1s, 2s, 3s, or so on, s orbitals L equals 0, p orbitals L equals 1, d orbitals L equals 2, and so on. So we can figure out how many radial nodes. Remember, the radial nodes are spherical, but if we know n and if we know L. So that might be decent multiple choice questions for the quiz in this chapter. How many radial nodes are there for a particular orbital, 4f or 3d or even 7d? And you should be able to figure that out based on what we've just said. And then the shape of an orbital depends on its angular and radial nodes. And we can plot that orbital based on its nodes, and we've seen the pictures and the examples that we've looked at already. And so the other question, that we get a little bit more detail on where the electrons are in these orbitals, or where the electron is in these orbitals, since we're looking at hydrogen, is to think about how dense the portions of the wave functions are between the nodes, where the probability of finding the electron is highest, where the probability density is largest. And so if we look at the 1s orbital, the 1s wave function, and we square it, we'll find that the maximum of that square, the probability of finding an electron, is largest at r equals 0. It's largest in the nucleus. And the question we have to ask ourselves is, does that make sense? Are we helping ourselves figure out what the electron's most likely to do by using that method? And with electrons in general, we're not. There's better ways to look at this. And that's what we're going to spend the rest of this lecture going over. Just to show that this isn't the best way to think about this, let's figure out what the probability is of finding the electron in the nucleus. So that's the next example problem that will work. What is the probability of finding a 1s hydrogen 1s hydrogen electron in the nucleus of an atom? And the nucleus has a diameter that's about 2 times 10 to the minus 15. That's about the width of a proton. And so we have our wave function. We know what our wave function squared is. It's easy to square since there's no imaginary terms. And the probability is going to be the integral of the square of the wave function over all space, 0 to 2 pi for phi, 0 to pi for theta, and 0 to how far out we want to measure the probability. So a radius of the nucleus, if the diameter is 1 times 10 to the minus 15, then the radius is going to be, if the diameter is 2 times 10 to the minus 15, then the radius is going to be 1 times 10 to the minus 15. And we have the wave function here, the normalization constant out here, or normalization function squared out here, square of the wave function. And then the dr and the rest of these terms come from the definition of d tau. And so if we go ahead and do, that's not a particularly complicated integration to do. So if we go ahead and do that integration, and you guys can work this out mathematically as well. But once we've done that integration, the probability calculation works out to 10 to the minus 24. So the highest probability density may be at the center, but it's not very probable to find the electron in that space. And so what might be a better way of looking at the electron's probability? And so we're going to introduce this new function called the radial distribution function. And let's put me up here where I'll be out of the way of some of the stuff that's going to pop up. If we use this function to calculate the maximum in the radial probability distribution, in other words, what's the most likely radius at which we would find the electron? And this is different from calculating the probability at a given point or at a given sphere around a point, because the larger the radius gets, the more points are on that radius. And so the probability of finding the electron at a particular radius might be higher, even though the individual points on that radius are smaller in probability than the smaller radii. And so if we use this function, probability dr equals r squared times the square of the radial function dr to do our calculation, again, we have our wave function. We only have the radial portion, but we will ignore the non-radial portions when we get up to ones that have angular portions, non-s orbitals. So if we square that, multiply it by r squared, we have our probability. And so what are we going to do if we want to know the maximum? Well, we could take the derivative and find out where the derivative equals 0, and that would give us the maximum. Or we could just set up a spreadsheet and plot it. And then we can see that the maximum ends up being out here at r over a0 is about 1.5. So 1.5 r, 1.5 a0s is about, 0.7, 0.8 angstroms. And so that's where the maximum probability is going to be. That's the most likely radius at which we would find an electron. And so think about that in terms of an essay question. I'll probably put an essay question related to that on your homework, and a computational question as well. And so that's the end of Chapter 9. Notice we did this in 3 lectures that were each less than 15 minutes. That probably equates to 3 class periods, because I do go much faster in these videos, but that allows you to watch them over and over again and pause and slow down and repeat things that you need to repeat, like we would in class, which would make these each take 50 minutes. So take your time, please, with these videos.